Samudravasane Devi Parvatasthanamandale Vishnupatnyai Namastubhyam Padasparsham Kshamasvami. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. Good morning, everybody.
Good morning, sir.
Morning, sir.
Last class, we had looked at answering some more questions related to composites as applied to flight vehicle structures. So we'll continue that process today. So today we'll be focusing on the larger length scale aspect. Most of last class was on the micromechanics, which is basically in the order of a few microns. That is, typically the fiber diameter dictates the order of magnitude of the mathematical model that we are considering. Now we'll move on to the macromechanics. We also saw the bigger picture in the previous class where we saw how these are all going to be related. The micromechanics that we did in the last class, the macromechanics that we will refer to today, and in between the mesomechanics, which is the connecting link between them. So having seen that bigger picture, we went into some of the simplest models that are available, rule of mixtures in particular, for the micromechanics. Now we will focus on the macromechanics. But now that we have learned these basic aspects, that is in terms of Y fiber, Y matrix, Y composite, now we are in a position to put them together, because in the micromechanics we also learned of this concept of the volume fraction. So based on that volume fraction, now we know how, given the properties of the fiber and the matrix, we can calculate the properties of the overall composite. So that property we are now able to determine. So I'll just put up a table from your textbook along with a few additional columns associated with the two of the material performance indices that we introduced. Of course, we introduced the stiffness in a form that is suitable for dynamics as square root of E by rho. But if it's only for a statics problem, then E by rho is sufficient, which is what I have listed over here in 10 power 6 meter per second squared, as you see over here, and in this particular column. And then in this column, you see sigma U by rho, that is the ultimate tensile strength along the fiber direction divided by the density, which is the specific strength as a performance index as opposed to a specific stiffness. Now let's compare and contrast these set of numbers that we have in the range of all the way from 24 for glass epoxy to 114 for a particular carbon epoxy composite. Now the textbook doesn't give the specific volume fractions for each of these. That's important in actually determining these values. So let's assume that it's somewhere in that range that we talked about, typical for aerospace composites, which is a fiber volume fraction of 0.4 to 0.6, and therefore a matrix volume fraction of 0.6 to 0.4, assuming there are no other additives or voids. Ignoring the porosity, which is always there, very small percentage though, if the manufacturing process involves autoclaves, for example, or vacuum bagging done in a proper way, vacuum assisted resin transfer molding, etc. But nonetheless, there will be a small amount of porosity, which usually becomes the source of matrix cracks, etc. Keeping all of that aside, we see that this is the range of the E by rho. So let's just compare that with what you have in your textbook for the metallic, conventional metallic alloys, which are used with aerospace structures, aluminium, titanium, and steel. Two typical aluminium alloys are used. The 2024 using a particular heat treatment, let's say T3, and the 7075, which uses a heat treatment T6. Now, both of these have an E by rho of the order of 26 in the same units, that is 10 power 6 meters squared per second squared. So that being the case, you see that is kind of comparable with what glass epoxy can give you. So glass epoxy is not going to give you a big jump in E by rho, or for that matter square root of E by rho. But you see that there are others like the carbon epoxy, and irrespective of which specific type of fiber that you choose and which matrix that you choose, because the epoxy is not clearly specified here. There are many different grades of epoxies, the aerospace grades of epoxies that are used. So that is also not very clearly specified here in this table in your textbook, but these are kind of to give you a ballpark understanding. So if you look at aluminium, it has 26, and this is glass epoxy is 24. But if you look at let's say titanium or steel, once again there's not much of a change. It's of the order of 25, 26. So they're all in the ballpark of S-glass epoxy. And remember that I talked to you about S-glass being the structural glass as opposed to E-glass, which is electrical glass fiber. So in all of these nomenclatures, there is always a slash in between two entities which are mentioned, specific entities. The first one being the fiber, and the second one being the matrix. So here you see that you have the fiber, carbon fiber, boron fiber, glass fiber, or aramid, and the matrix in three of the cases is epoxy, which is a polymer matrix composite, or leads to a fiber reinforced plastic, whereas this is a MMC, or what is the abbreviation for metal matrix composite, where aluminium, a metallic alloy maybe, could be used as the in this case, yes, 2024 is an aluminium alloy. So here you do see in the case of carbon epoxy, the specific epoxy that is mentioned over here, 5208, 3501-6, etc. In the case of glass epoxy and aramid epoxy, which is Kevlar, basically. Kevlar 49, which is the superior one compared to Kevlar 29 when we looked at all the fibers. So now, here the specific epoxy is not mentioned, but nonetheless these would not change way too much because they are dictated primarily by the fiber properties along with the volume fraction of the fiber, which we assume is in the range of 0.4 to 0.6, 40 to 60% of fibers. So now you see that S-glass is kind of comparable with the metallic performance as far as a stiffness-based design is concerned. So if deformations are the one which is most critical, you might as well go for metallic alloy if that is a cheaper option or more readily available option, rather than even glass epoxy for that matter. But if you're looking at a stiffness-based design, which is much more critical, then you would choose something like the IM6 and 35016 as the matrix and the fiber. Now, so the results will be comparable in the case of the square root of E by rho, dynamic stiffness design as well, when natural frequencies become the more critical thing that you want to deal with. The next thing is the strength design. If you look at the strength design, and these are in the range of about 566 for boron aluminium, which is fairly low, all the way up to 1845, once again for IM6 35016. So now this is in a unit which is again meters squared per second squared, but 1,000 factor is taken out over here instead of a million factor over here. So that is basically what you have over here, because the stiffnesses are typically of much larger magnitude, usually measured in gigapascals, as opposed to sigma u, usually mentioned in megapascals, though here it is given in gigapascals over here. So you would see that order of magnitude difference between these two. But in most cases, we are looking at square root of E by rho as the performance parameter, in which case the square root of 10 power 6 again becomes 10 power 3. So it's not going to be of much of an issue over there. Now, of course, the unit will change. It will become meter per second instead of meter squared per second squared. So that is the range. Now let's again compare with the typical metallic alloys that you have. The sigma U by rho is in the range of 162 to 194 for aluminium, that is 2024 and 7075. And then for titanium, it is 207, slightly better, and steel becomes even better, and even in a specific strength based design at 229 to 238. But you see that these are way ahead of that. So though in terms of the absolute strengths, there may not be sometimes too much of a difference, because you can have steels which go all the way up to 1860 megapascals, that is 1.86 gigapascals, and that is kind of comparable with most of them except for these two carbons. So you'd see that in terms of the specific strength design, there's a big jump all the way from hundreds and 200s for the case of metals to all of the order of 1000. In this case it is smaller because it's a metal matrix, so it's kind of comparable. But even there, if you compare to a typical aluminium, which is 162 to 194 range, the introduction of the boron fiber has increased it about 2.5 times the original value. So that's a big increase as well, just by introducing boron fibers within 2024 aluminium alloy. So this is what is very critical in terms of the longitudinal properties of the composites in the tensile applications. Keeping this in mind, and again, of course, these are based on the densities which are given in your textbook in a gram per cc, but you should of course use kilogram per meter cube, that is the SI unit, which means all of these will get multiplied by 1000 before they're divided by this, and giga of course involves a 10 power 9. So those factors have to be taken into account in calculating these factors and the numbers that are there over here. Now, let's also talk about the other typical alloys, because aluminium we mentioned 2024 and 7075 as the ones which are commonly used. So as your textbook says, the main difference is in terms of the particular components in which they are applied because of their slightly different properties. And you can see that the Young's modulus rarely changes for any given type of alloy. Most steels will have around 210 and most aluminium alloys will have around 70. So in this particular case, what is listed in your textbook is about 72 gigapascals as the Young's modulus for 2024 T3 and 71 gigapascals for 7075 T6. So it's only in terms of the ultimate tensile strength you see a difference between the 2024 and 7075. In the case of aluminium 2024, it is 449, whereas in the case of 7075, it is 538. So as your textbook says, there are two different heat treatments which are typically used with 2024, T3 and T42, in terms of how the metallic alloy is actually processed. And irrespective of those two heat treatments, in both cases, the 2024 has excellent fracture toughness and slow crack growth rate, as well as good fatigue life. So that makes it applicable in certain locations like the fuselage, for example, and the lower wing skins, because they are prone to fatigue because of the cyclic tensile stress that is there. Because the lower wing skin is what is predominantly under tension, except on the ground where very small amount of compression is there because of the self weight of the wing. But otherwise, it's predominantly under tension, and that value of the tension keeps changing depending upon the phase of the flight and in particular the load factor that is involved. That is how many times the weight of the aircraft is the lift. So based on that, it changes. The self weight of the wing is much smaller compared to that, n times L, that is load factor n times the lift. And therefore, that is the dominant load that is there. Of course, there's a drag, the pitching moment, etc., and the weights of the engine that is overhung, etc. But nonetheless, most of the bottom skin of the wing is undergoing tension, which is changing with the phase of the flight, and which means fatigue. So basically the stress, the tensile stress, is changing with time in a cyclic manner, and the number of cycles that it can last in terms of retaining its strength and stiffness is what determines how good it is in fatigue, and 2024 is excellent at doing that. On the other hand, you have the 7075, which has a higher strength, about 538 megapascals instead of 449.
Hello.
Yes.
Sir, I think your slide is not changing because some of the data which
no, it's just in your textbook. I have not put the data in the slide. So I'm just contrasting these numbers with the numbers for the composite, which is what is more critical for us. So just a comparison is what I'm saying. I don't have a slide for this. So you can actually go through your book, page number 15, to see some of these properties that I'm discussing in a summarized form. Because, as I said, we'll be dealing with metals as a special case in analyzing composites by converting the anisotropic and non-homogeneous nature to isotropy and homogeneity. So I just want to very briefly rush through the metallic alloy properties vis-a-vis the composite properties that you're seeing on the slide. Okay. So the 7075, on the other hand, has a higher strength of about 538 megapascals compared to 449 megapascals for 2024. And because of the higher strength, it can be used in certain applications which are, of course, this is a tensile strength, but in compressive strength, it's even better. So it would be used in those regions which are subjected to compression. So in the case of the wing, it's the top surface because of the lift being fairly large. So you have the top undergoing the compressive loads of the bending stress. So that is where the 7075 is typically used. So for the upper wing skin, which is subjected to compressive stress, where fatigue is a less of a problem over there. So because the fatigue properties of the 7075 are not as good as the 2024. So these are sometimes give and takes that you have to do in deciding upon a particular material. When you have a choice of, let's say, two, one would be good for based on certain properties, the other would be better on certain other properties, and then you see which property is more significant for a particular application. So that is the example that I gave in terms of the lower wing skin and the upper wing skin. Yes, the upper wing skin also undergoes a little bit of fatigue, but the range that you have in the variations of the stresses is not as much as for the bottom, which is the reason why fatigue is even more important at the bottom, tensile loading, rather than on the top, which goes into the compressive regime as well. And therefore, it would not be, even with a slightly smaller fatigue life, it would be okay to use the 75 T6 over there compared to the 2024. So that is an important thing. There are also important alloys that are being still developed. One, for example, is now already in place for some applications, is when you use lithium as one of the alloying elements along with aluminium, and there you would have an increase in the stiffness of about 10% and 10% lighter as well, because lithium is a much lighter element, as you know, appearing very early in the periodic table. So 10% increase in the stiffness and a 10% reduction in the density means that you are having a 21% increase, because 1.1 into 1.1 about 1.21, which is 21% increase in the static performance index for stiffness based design, which is E by rho. So these are the things that I would like to just contrast between the properties of composites vis-a-vis this, because in an earlier class we looked at just the fiber properties, and it looked phenomenally great compared to the metallic properties, but that cannot be of any great significance because you can't use the fibers by themselves. Now we have reached a stage where we have talked about why fiber, why matrix, why composite, where composite as well, and we have also looked at, given the fiber and matrix properties, how you get the composite properties. So at this stage it's important to understand that these are the properties that we need to compare with those of the metals, not the very high idealistically sounding properties based purely on the fiber. But nonetheless, in spite of the reduction because of the introduction of the matrix in these specific properties, E by rho and sigma U by rho, still you have a huge advantage compared to metallic alloys. But the even greater thing, which I have not put up here, is the E by rho cube, that is for the stability based design, where compressive loads are critical, and therefore a possibility of buckling is there. E by rho cube will be the determining factor, and there you would see that there's almost an order of magnitude difference between what you have for the composites vis-a-vis the typical steels, titanium and aluminum alloys that are used for So now, based on this, you have a homework now to look at these parameters that we discussed. That is the strength-based design was governed by sigma ultimate tension divided by the density. So that's in a unit of 10 cube meter squared per second squared, which is what we used in the previous slide as well. And the stiffness based design in a dynamic situation becomes a meter per second, but now again 10 power 3 is a factor which is taken out. So this is for dynamic case. So I want you to focus on this dynamic stiffness design. And then the buckling design, or rather stability design to avoid buckling. So E by rho cube, which is having the unit of strange unit of meter per 8 by kilogram squared second squared because of the cubic density that is involved over there. The reason why I'm listing out these units is because for a comparative study, you need to keep all of these units consistent, and the factors that you take out, like 1,000 factor, etc., should be consistent throughout the class. And for each one of you submitting the assignment, this is an individual assignment, not a team assignment over here. So you would have to individually submit, and then we would see the comparison. So if it would be easier if you all use the same SI units along with the factor of 1,000 taken out for the strength performance index and the stiffness performance index, but given as it is for the stability based design. So what is the homework? You're required to once again go through a web search and or a book search. There's also a very good website that some of you might be aware of for all material properties called matweb.com. MATWEB, standing for materialweb.com, which lists a lot of useful properties, some beyond the consideration of this particular course, but for very specific choices of materials. Like for example, in today's class we discussed the 2024 7075 with various heat treatments for the aluminum alloys. We discussed the various epoxy grades for the case of the carbon composites. So for each one of them specifically, the properties will be listed. So that's a good resource. But I want you to not just restrict yourself to matweb.com, but also look at many other possibilities. Some might give you very high properties for whiskers. If you do find them, you'll include them, but do mention that it's a whisker. And as we discussed in a previous class, whiskers being of the smallest diameters that you can go to with the current technology for reducing the fiber diameters would not be possible to be made in very long dimensions. The fiber lengths will be short, and so you typically will have only short fiber composites, which might be okay for certain applications but may not be for others. So if you do include whiskers, let that be beyond these 5. we are only talking about those which are not viscous, which can be drawn out into long fibers, because that is what is more critical in making prepregs and fabrics for composite structures typically used in flight vehicle structures. So find top 5 fibers each. When I say top, based on each one of these criteria. So 5 for the strength design, 5 for the stiffness design, 5 for the buckling design. There might be some which are kind of common for the 3, might not be the topmost, but one of the 5 might be sharing this. But I want you to find the top 5 that you can basically find for each one of these criteria. So and all of them I want you to use to start with an epoxy composite. And I'll give you the properties of the epoxy that you need to use with this. Let's use a volume fraction of the matrix of 40%, and therefore the fiber volume fraction would be 60%, ignoring the voids and other additives. And then we want these 3 to be maximized, and as I said, restrict yourself to these 3 units so that we have a good comparative study which is possible. And so this is an individual assignment, so points will also be given to a comparative result between students. So the TAs will take into account all of the properties that each one of you give. So I would suggest that you all give it in an Excel sheet so that they can kind of combine and very easily compare across the class which is the top 5 for each one of these. And then if you have found some of them, then you get a few bonus points. The reason why I want to do this comparative study is because I want you to be as exhaustive as possible in your search, as comprehensive as possible, so that you find that. And the other important thing is, when you choose a fiber, make sure that it is compatible with epoxy matrix. So in other words, if it's chemically reacting with epoxy or does not mechanically gel with epoxy, then it's not a good fiber to use, because the interface between the fiber and the matrix will become the weak link, and stress transfer would not take place between the fiber and the matrix, vice versa, and therefore it would not act as a composite. It would just act as 2 separate materials placed next to each other, which could probably slide over each other with some friction might be there. So chemical compatibility to some extent, also the mechanical compatibility. Mechanical compatibility in many cases can be taken care of by appropriate surface preparation of the fiber, in terms of either having a certain roughness introduced through the coating or something like that. And even chemical compatibility, if it's not there, sometimes can be introduced through coating. So do mention those aspects if you do choose those which by themselves, the fiber and the epoxy, are not compatible with each other. So this is what it is, and the properties that you need to use for the matrix, which is the epoxy matrix, would be 3.4 gigapascals. The Poisson's ratio would be 0.3, and the density of the matrix, that is epoxy, is 1200 kilogram per meter cube, because you'd need all of these properties in calculating some of these. You may not need the Poisson's ratio right now, but it will be essential for some other thing that I'll be talking about a little later. So right now these 2 would be critical, and we would use the rule of mixtures formula that we got in the previous class, not only for the Young's modulus but also for the ultimate tensile strength. Whether it is valid or not is questionable, but that is what only thing that we have learned, and that is the simplest model which is well within the scope of this course. So we will not go into trying to identify the actual ultimate tensile strength of the composite in a more reliable fashion, which will be much more mathematically involved. It could involve a lot of empirics as well, based on experimental results, etc. So that's beyond the scope. So we will use the same rule of mixtures formula. There is a weighted average of the Young's moduli that you had, the weightages being the the weightages being the density, the volume fractions of the fiber and the matrix. So on the same kind of formula would be used for the ultimate tensile strength in terms of the ultimate tensile strength for the fiber along the fiber direction. Because some carbon fibers will have different properties along the transverse direction. So there is an anisotropy not only at the composite level, but there can be an anisotropy for some fibers, not all fibers, at the fiber level also. So do take the appropriate sigma ultimate over there. And then, of course, the weighting factor is one and the same for either it is for E or for sigma U, and for rho as well. Okay, so I want you to repeat this with an aluminium matrix. This time take aluminium 2024 T3, which is what, for example, is used with boron, as I showed you in the previous slide, a boron fiber. So you repeat this whole exercise with the aluminium matrix. The reason why this is important is this can take higher temperatures, and a lot of applications within the aerospace are in the higher temperature regime. So an epoxy matrix may not be suitable there. The next best that you can go for is an aluminium matrix. Even better would be a titanium matrix, etc. But let's restrict to aluminium 2024 T3, whose properties are given in your textbook. So use the same properties that are given in your textbooks, which is 72 gigapascals for the Young's modulus and 449 megapascals for sigma U. So this is what is given in your textbook, and your textbook is available. I'm sure most of you would have already seen it as an e-book, freely downloadable, unlimited, in the IAC library. So I've ordered this as well as many other books related to flight vehicle structures. I'd shared the entire list in the beginning of the course, so you can go to the chat and the top of the chat to look at those books as well, but those are all pretty much references. We'll mostly stick to this particular book, and so I want you to take the E and rho from there, the sigma U, and also rho, which is the density, will be 2780 kilogram per meter cube, which is what is listed in your textbook. So use those properties for the aluminium matrix. Once again, use a volume fraction of 40% for the aluminium matrix and 60% for the top fibers that you choose. So the fibers that you would get in these two cases would be quite different, because what is compatible with epoxy may not be compatible with aluminium. Sometimes they might be, and there might be some commonalities as well. So you do look at all of those aspects in arriving at your conclusion. Oh, sorry, I thought I had given. Okay, just ignore this slide. 71.3 and 2700, I think I just gave ballpark values. Ignore these values. Take the values from your textbook, what I said. That is, instead of 71, it is 72. Poisson's ratio is not required for this particular example, and the density that you have is 2780. Also, you would probably need the tensile strength for the epoxy, which I have not listed over here. So I request one of the teaching assistants to look at a particular epoxy to give the sigma U for the intention for the a particular epoxy as the value that they can all use for the calculation using the rule of mixtures. So please send that information to the students, because they'll need that information as well, sigma U of the epoxy matrix. But for the aluminium properties, just use the ones in your textbook for 2024. Are there any questions on this assignment? So I think the TAs have been telling you this quite regularly. Citations are very, very important. I think Vignesh has brought about this point, Rajesh as well, in many contexts. The citations are very, very critical. So as you go forward, either towards research or even presentations at conferences, etc., which you would do even if you're not an academician, even as an industrial researcher, giving the appropriate references, the primary references, is very critical. So do cite all references that you get the properties of these top 5 fibers from, and be very specific. I think that is also very clearly mentioned by one of the posts that the TAs made, in terms of giving the not just the overall website link, but the specific web page in that website from where you got that data. So it's critical that you mention all those references so that it can be cross-verified. Okay. Now we get on to the one of the most important and probably interesting parts of the course, where we are getting into the nitty-gritties of the modeling. And this is something which is kind of ignored, or at the most touched on a very superficial level in most structural analysis courses. But assumptions and thought towards what assumptions are made, and whether they are valid or not, whether they're required or not, are very, very essential aspects. And what is the influence that those assumptions have on the actual derivations and the end model that you develop is very important for any student to understand while doing a derivation. Not only listing those assumptions, but in terms of their validity and their effect. So it's not just about composites. Anything that is modeled, how is it modeled? By making assumptions, because we are moving away from reality to a model. That's why we call it modeling. Okay, a model is not the reality. We can go as close to the reality as the current state of the art permits, both in terms of the physics as well as the mathematics. You can push the limits, make it much more rigorous, much more in terms of the derivation, mathematics of the derivation, as well as the starting point of the physics that you use to make the derivations. You can push the limits. You might end up with a much more complicated model, but still, nonetheless, at the end of the day, it is a model. And you will always see that there are certain cases where tests in reality, either at the lab or in flight tests, will disagree with whatever results you get based on applying these models that you develop. So making assumptions is what is the underlying factor in any modeling process, be it for composites, be it for any other metals, or any mathematical model, not only restricted to structural analysis, but fluid analysis or fluid structure interaction, controls, whatever. So as a good researcher and as a good student, even if not doing research, you should always question these things. And two important questions related to assumptions are the necessity factor and the relevance factor. And these could be different. I'll give you examples of these as we go forward. First thing is, are all these assumptions necessary? See, sometimes even in textbooks, unfortunately written by some really otherwise great researchers, you would see that there are certain assumptions which are listed. Even if you don't make those assumptions, you would end up with the same model. So why even list that assumption? Without that assumption, sometimes you can end up with the exactly same model. So is it at all necessary to make that assumption? That sometimes we have to explore. So if it's not necessary and you still end up with the same result, you might as well drop that assumption, because otherwise you would think that your model is restricted to certain classes, but it might actually be more widely applicable. So make sure that it's really necessary in order to come up with your end result. Otherwise, drop it. So the second aspect is in terms of the relevance, which is where the validity of that model eventually gains strength from or weakness from. So is it a relevant assumption for that particular class of problems that you want to eventually apply that model to? So in our case, we are trying to develop models for composites, and using that as the special case of that as for metals, as long as it is within certain limits. So is it applicable for all of them, and where is it not applicable? If it is not applicable, where does that limit, where is that limit breached? What is the threshold? So these are the things that we need to answer, and try to make it as broad based as possible for the class of problems that you're applying. Sometimes you might have 2 or 3 different models, or a finite number of models for different classes of problems within the same kind of application, and you choose which particular model to use depending upon certain factors, certain flags that you might have, either manually or built into your computational programs, so that it is done in an automated fashion. Once it recognizes certain flags, yes, it is the model A that is to be used instead of a model B or model C. So that kind of classification is possible. But if you can have a single model which can take care of that entire class of problems that you're going to deal with, that is probably the best, so that you don't need to make these design choices based on the flags. But more often than not, that is not feasible, because you have a wider range of material and geometries that are applied, and you need to ensure all of these are taken into account. Now, before we go further, let's also revisit the fact that we talked about dimensionality. We said that all the structures, flight vehicle structures, or for that matter any other structures that we are dealing with, are in three-dimensional space as we see it. And many a times you have those three dimensions, one of the dimensions either dominating or being dominated by the other two dimensions. So when one of the dimensions is dominating, we call it a one-dimensional model. So what specifically we mean mathematically by this is that just one independent variable is sufficient to determine this problem. So that's where you have a beam or a column or a rod, or you have a shaft. All of these are examples, or even an element of a truss, an element of a frame. All of these are one-dimensional structures where the cross-sectional dimensions are over-dominated by the length dimension of that rod or column, whatever you have. So therefore, if you call that dimension as, let's say, x1 along the length of that rod or truss element or frame element, then x1 becomes the only independent variable. So we're going to talk of two sets of variables, dependent variable and independent variable, that all of you are familiar with. So if you have y is equal to y of x, for example, y is a dependent variable, x is the independent variable on which y depends, and we are basically generalizing that. So if that number of independent variables is just one, you call it a one-dimensional problem. Then you get on to two-dimensional problems where you have one dimension, that is the thickness dimension, being dominated by the other two dimensions. So you end up with plates or shells, and therefore x1 and x2, which are along the surface of a shell, x1 in one direction, x2 in many cases chosen for convenience to be an orthogonal direction, but the only requirement actually is that those two directions should be not collinear or not parallel to each other. So that is basically all that is actually required. And but you do have x1 and x2. The x3 dimension dependence is removed in a certain way. So it's not that it is not there, it is still there, but it is removed in a certain way, so that the major dependence now is only on x1 and x2. Same way for the rod, the x1 is all that matters now. The x2 and x3 cross-sectional dimensions do not matter, in the sense that we have reduced the cross-section to a point. Same way in this case, we have reduced the finite thickness to a zero thickness, or just a surface or a plane. Plane in the case of a plate, and surface in the case of a shell. So, and typically this is chosen as a mid surface or a mid plane, but need not be, it could be any one of those. So but the essence is that now you have two independent variables to deal with, x1 and x2, instead of just x1 in the case of the rod. Then you go to three-dimensional structures, which is what in reality everything is, and there you have x1, x2 and x3 as well, which is basically getting into a 3D space that you are talking about. But when you go into other aspects of mechanics, like relativistic mechanics, for example, you're going to talk about space-time. And the space-time field, you bring in time also as an independent variable, and which will be essential in many of the dynamics problems that we will be doing, even in classical mechanics, to bring in time as the fourth independent variable. So in a mathematical sense, you're now talking about a four-dimensional space, x1, x2, x3, and time. And very interestingly, even in ancient Indian scriptures, the word kālā is used not only for time that most of you are familiar with, but in certain aspects, it's used for space as well. So space-time is usually referred to as kālā. So there is, it's not just for mathematical modeling, but in terms of the overall behavior also, you would see whether it's in special relativity or general relativity, etc. There is this concept of space and time both being independent variables, can have somewhat similar behavior in terms of how they affect various things. So you can generalize from a three-dimensional space to a four-dimensional space to deal with that. But in the mathematics that eventually would be very, very important for a lot of applications, we may not see too much of that in this course, but you would definitely see in some other courses as you progress through your MTechs, and those of you who are doing PhD definitely in your research, where you're talking of an n-dimensional abstract space, and many of these results that we are developing here can be extended to that n-dimensional space. And so a lot of carryovers from here would be there. So, but then you can no longer visualize this. In fact, even when you go to a four-dimensional space, it becomes impossible, if not too difficult, to visualize these things. But as you go for larger and larger dimensions, it becomes even more difficult. So let's keep all these things in the background in terms of an understanding. So you're going from a beam like 1D structure to a 2D structure, plate or shell like a 3D structure, where all three dimensions are important, spatial dimensions, and dynamics problem, which could involve vibrations, for example. It could involve fatigue, it could involve impact, which is an instantaneous load that is applied of large value. So in all these cases, you would have a time dependence coming in some way. So that is an independent variable as well, leading to a four-dimensional space. But for all practical purposes in this course, we will restrict ourselves to start with three-dimensional structures. So three spatial dimensions are involved. So we will introduce certain notations which involve tensors, which will involve the components of that. Yes.
Vignesh here.
Yes, Vignesh.
So whenever time is involved, we speak about the reliability of a material, right? Mm-hmm. So let's say the Weibull distribution or the fatigue SN curves, mm-hmm. or how long will a material withstand, mm-hmm. Or the lifetime of a material, right?
True. Yes, Vignesh.
Yes, sir. Can you hear me?
Yes, I can hear you. So that's right. What
we
you're saying.
We regularly discuss the lifetime of a material, right? How many life cycles, mm-hmm. or how many kālās can it withstand, or something like that, right?
That's right. That's right. Is that all your question is?
Yes, sir.
Yeah, absolutely. Yeah. So it's very important that you brought that the cyclic aspect into picture. So where the kālā is coming into picture, but it's also in terms of not only the time, but the kālā is also in terms of the space. So you see that that's the reason why I've always been mentioning, when you want to consider a particular structure like this as a beam, for example, you can do that only if the cross-sectional dimension is small compared to the wavelength of deformation, not the actual geometric length, which is about 15 centimeters, let's say in this case. So now it's not that what we are referring to, but the wavelength of deformation. So there is a cyclicity that is involved in time that you're talking about in terms of a kālā. There is a cyclicity which could be involved based on the vibrations, dominant modes of vibration that a structure is going through, which involves a kālā in the space as well. So that's why a lot of things that you talk about in space or in time can be generalized to the other purely in terms of a mathematical model. The exact behaviors will be different, but many things in terms of looking at it from a purely mathematical point of view are very, very similar. So it's good that you brought that cyclic aspect into picture, because fatigue is typically measured in terms of an SN curve, fatigue performance, and you want a higher strength strength at any given value of the number of cycles of fatigue that it has gone through. So an SN curve which is higher for one material compared to the other would be preferable as long as all other things are maintained the same. What you're talking about is in terms of, yes, there is a strength reduction, but how much of strength reduction are you willing to allow? How much of, to some extent, small extent, the stiffness reduction are you willing to live with? So that's all based on the criteria that you have. And so aging is something that is involved with that. But also, another important thing that you would see is in terms of other kinds of loading, like let's say thermal loading and thermal fatigue that is involved with that, and that can result in creep or permanent deformation that is there. So how much of permanent deformation are you willing to live with? So the property reduction on the one hand and the permanent deformations that might result, whether you go for very high temperatures or you go for the fatigue mechanical loading where there's a property reduction. Yeah. Okay. So now let's go forward. Let's start making these assumptions. I will list out 10 assumptions. The first assumption is that the material that you're going to deal with is an elastic material. So let me deal with this. Okay, so this is the first assumption that we are dealing with, that it is an elastic material. So what does this essentially mean? Anybody want to answer? What does elastic material mean?
Deformations are within the elastic limit.
Okay, very good. Can you repeat that?
Up to the elastic limit.
Okay, that's good. So what you're basically saying is that if you plot a stress versus strain curve, you're basically having a region where if you do the loading, you go in this direction, and if you do the unloading, you're coming back in the same direction, right? So this has to be further qualified in terms of a specific component of the stress and a specific component of the strain. So let's call this as epsilon KL and this as sigma IJ. Okay. So for example, if you're plotting sigma 11 versus epsilon 11, you get the typical tensile longitudinal direction stress strain behavior, or what we call as the constitutive law. I've drawn only part of it. How it varies beyond will depend on the specific materials that you're dealing with. So this is basically what you mentioned by elastic. So what is it? So this is more from an empirical point of view, from a graphical point of view, or even the experimental results. How is this curve obtained? You perform a simple uniaxial tensile test, for example, and you keep monitoring the load that is applied, use a strain gauge to monitor the strains that are there, and then in different directions, and therefore you can arrive at many different combinations that you have for the stresses versus the strains that you have. So this sigma ij and KL, so these are Latin indices that I'm talking about over here, and all Latin indices, unless otherwise mentioned, will have the range 1 to 3, because we are talking about a three-dimensional space over here, and so we are talking about these being in that particular range 1 to 3. And if I use them in a repeated fashion, then there is an implied summation, what is known as the Einstein's summation convention, which we will see shortly. So in this, you see that since I and J are potentially having 3 different values, so you have 9 stress components and you have 9 strain components that are there in general, having fixed a particular coordinate system in which they are measured. But otherwise, what these essentially are basically second rank tensors. So which is why you need 2 subscripts for them. So the stress is actually in the form of a second rank tensor, the strain is also in the form of a second rank tensor. What does a second rank tensor mean? Of course, people interchangeably sometimes use the order and this rank in the case of tensors, but we will stick to saying that the rank is given by for our practical purposes. There are more rigorous ways of defining it. How many subscripts you need to define its components would basically determine that. On the other hand, a vector, for example, if you have a force, let's say a force which is applied, let us say over here, so that force has a magnitude and it has a direction, and it can be represented by a single or first rank tensor. So that is basically what it is. It involves one particular direction. That is sufficient. Whereas for a stress, you need two different directions. We have seen this already. The plane on which it acts and the direction in which it acts on that plane. So first, to identify the plane, we need a direction which is usually used in terms of the normal to that plane, and then you have the other situation being the direction within that plane on which that stress acts. So unlike a force, which is a first order or first rank tensor, as different terminologies are used in different places, we will use the terminology of rank over here. So in that sense, because two different directions are involved, whether it is the stress or the strain, so it is a second rank tensor, and we will typically denote that by a double underline as opposed to a vector which we will indicate by a single underline. Of course, some people indicate it by a, let's say, an arrow on top, or by using bold fonts, which is useful in printed material but not in what we write, because it requires rewriting over that over and over again. But so various other things are there. So we are basically generalizing a first order tensor now to a second order tensor where we need two directions. Now it's very easy to go back and see what is a scalar. Like, for example, your density that we are talking about in your homework is a scalar quantity, mass density. So you're talking about a quantity which does not have any direction at all. So it's basically an example of a zeroth rank tensor. Okay, so this is density. So which means that no direction or zero directions are involved. Only magnitude is sufficient over there. On the other hand, the force is here shown over here is an example of a first rank tensor, because it requires one direction, which is the direction in which the force is acting. On the other hand, now we are talking of examples over here of second rank tensors, where you need two directions in order to define them. We saw that example in the case of the stress. One direction involves the plane on which it is acting. The other is on that plane in which direction is that stress acting. That is what your I and J basically refer to in a respective sense. So I refers to the plane on which it is acting, and J refers to the direction on that plane in which the stress is acting. So this is what we have in terms of an understanding that is required from this particular course's point of view. Of course, there are much more rigorous ways of defining these. We will not go into those details right now. For our purpose, this actually is sufficient. So now what we mean by elastic, we have seen from an experimental point of view over here. But now we are interested more in seeing what is elastic from a perspective of mathematics that is involved. So now what we are saying is that this sigma is a function only of epsilon. So in other words, given epsilon, I know sigma, and in a particular coordinate frame system that is fixed, let us say, x1, x2, x3, you have basically 9 components of strain and 9 components of stress that you have, and those relationships between those is what we are saying is a one-to-one mapping. In other words, given an epsilon, there is a unique sigma, and vice versa. Given a sigma, there is a unique epsilon that is over there. So this is what elastic means. And how does that relate to what we talked about here as the loading curve and the unloading curve? It basically says that there is only one curve. In other words, there is no other curve which is coming down over here leading to a permanent deformation, for example, or may not be. So it could still be coming back to the original, but it might be following a different path. So in other words, there is no different paths that are involved. It's all happening on the same path, because for a given set of epsilon k else, of course you have 9 into 9, 81 such plots. This is not the only plot that we are talking about. We are talking of 81 such plots, and each one of those plots is having a behavior like this, that it is loading and unloading along the same path. So that is what we are talking about over here, keeping all others 0, varying only one of the strains and seeing how the stress behaves, or vice versa, keeping all the stress components except one to be non-zero, to be 0, only one to be non-zero, and then seeing how all the other strains can be probably measured using various options that you have experimentally, and plotting them and seeing that the loading and the unloading curves are one and the same. So these are the two things that are very critical over here. Now, so this is a tensorial equation. The same thing can be written in terms of your tensor components, that is your sigma ij is now going to be a function sigma ij of only your strains. Of course, all the strain components, but nothing other than the strain determines it. Now, there are many implications to this. So what are those implications? One fact is that we are talking of a local model. In other words, what happens here affects only what is going to be the behavior of the material at that particular location. Anything around that, whatever is happening, is not going to affect it. So in this particular structure, if I take this particular point, then you're basically looking at that particular point, what is actually happening. The strain value is going to entirely determine the stress at that particular value, all the components. On the other hand, what is happening even in a close by area region is not going to affect it. What are known as non-local effects. So in other words, the local model is actually kind of implicit in this, but not necessarily, because there can be non-local elasticity as well, but we are restricting ourselves to not only elastic model but local elasticity over here. Okay, so what this basically means is that we are talking of here at this point where the stress is measured, where the strain is measured. Only these two are related, nothing in the neighborhood or farther away as well. The second aspect that is important over here is the fact that you are now talking about the independence from a time history. So in other words, there's no memory that is involved. So what that basically refers to is, at this instant, whatever is the strain that is there, that is what determines the stress at this instant. What happened to the strain in the past is of no consequence. What happened to the stress in the past is of no consequence. At this time, is this the strain? So therefore, this is the stress. So in other words, we are now talking about now. So basically what we are essentially doing is, we are talking of here and now. So both this is basically in a spatial sense that is here, and this is in a temporal sense where we are saying now, right? So you see that spatial sense in general can involve x1, x2, x3, and the temporal sense basically involves your time t, right? Now, this is what we together refer to as the space-time model, or what is congruent to kālā, right? So this is basically what is saying is that what is the history is not affecting it. So this basically leads to what is your karmic theory. So you're saying that what you did in the past, what you spoke in the past, what you thought in the past, these are going to affect what you're doing now. But no, this kind of specific material that we're talking about is unaffected by what it did in the past. So in other words, it's beyond the karmic bondage that we're talking about. So that is basically the essence of this elastic local model, which is not having a memory. So for example, you're ruling out certain things like shape memory alloys, for example. Shape memory alloys have a certain memory that they carry with them. We'll not go into the details of that. So at austenite and martensite phases, and then the temperature cycles, the loading cycles, all of that it remembers, and therefore its behavior changes along with that. So the question is, do you use shape memory alloys all the time? No, it's an overkill. You don't need them. So when you need the shape memory alloys for certain applications, you'd use them as a smart material and as an actuator, for example, in certain applications. But then for most cases, you do not. So the whole idea is to understand that memory is an important thing, but it is not always necessary. When you want to use the memory, use it. And when you don't want to use it, you put it aside. So that is basically what you're trying to do with the local elasticity non-memory kind of a model, where you're focusing on here and now. That here and now is a very, very critical aspect, because then it is saying that this moment is inevitable. So whatever is happening at this moment is what it actually is. You accept that moment as it is because you do not have a choice. That's the only possibility, to be in the present for this kind of material, because it has gone beyond that stage of the memory affecting it and the neighborhood affecting it. What does that mean in terms of a human being, in terms of the neighborhood affecting it? You are basically concerned about other people's opinions. All your neighborhood, what it thinks of you, you're concerned about that. As long as you're not concerned about that, you're going into a local model where all that matters is what happens within you. And the same way, what happens at this instant is what is governing all that is happening over there. So in other words, in this expression that we wrote, sigma ij equal to sigma ij of epsilon kl, we are not taking into account an explicit dependence on the xm, that is the positions, and the time. Where again, m also being a Latin index, all Latin indices, as I said, as I showed over here, I, J, K, L, M, etc., vary between 1 to 3. Later on, we'll introduce Greek indices for certain applications, where we will say that the range that they have is 1 and 2. There will be no, the third direction will not be there. So whenever I use Latin indices, unless otherwise specified, I, J, K, L, and M are varying from 1 to 3. So what we are now saying is that this dependence on xm and t is not explicit. So you see what I wrote over here. So this dependence on xm and on time is through epsilon kl, because epsilon kl is a function of time, is equal to epsilon kl of xm and time. right? Same way, sigma ij is also a function of xm and time, but its dependence on xm and time comes through epsilon kl. Because epsilon kl is depending on xm and time, therefore sigma ij is depending on that. Let's not confuse with the vector which we denote by a single underline. So now you see that this dependence, one-to-one mapping between the strain components and the stress components is what is the essential aspect of the model that we are considering in terms of an elastic model, which is local and which doesn't have a memory. So what are the other options? There are certain non-local models of elasticity where at a point the stress and the strain depend on what is happening in its neighborhood. So those neighborhood areas, and the more the accurate the model, it will take a larger neighborhood into picture, but for all practical purposes a reasonably small neighborhood is good enough to understand that. So then you lead those taking into account what is happening in the neighborhood instead of just what is happening here is what leads to non-local models, which is beyond the scope of this course, but we are just introducing it to see that what are the assumptions we are making, is it valid for the kind of materials and structures that we are dealing with, is all that we are trying to see over here. Aspect is that we are also saying that it in the sense of time, it is basically dependent only on what is happening at this particular instant, because what had happened before can, for example, if it is a creep kind of a loading, could have reduced its properties. What Vignesh pointed out in terms of an SN curve, if it has gone through a few fatigue cycles, its strength could have dropped. Are you taking all that into account? No. So that's what you're basically doing in this particular case, that you're saying that the history doesn't matter. Whatever is the strain at this point of time at this particular location, that alone determines all of the 9 components of the stress given a particular coordinate system that I want to measure. So is this clear in terms of the description of elasticity from the perspective of what we will do in the course hereafter? If there are any questions, I'd be happy to answer that.
Sir, this is Amanwar.
Yes,
Sir, what do you mean by the neighborhood? Neighborhood means suppose we are taking a point, so the stresses at that point should not be dependent upon the stresses at the closest point. Are you saying that?
Yeah. See, again, we have to go into details of the non-local theory in order to understand that, which is way beyond the scope of this course. But the size of that neighborhood, what we are saying is that is usually very small. Again, I'm talking in a qualitative sense. You have to actually quantify that in terms of orders of magnitude, in terms of something that is there. For example, if it's a fiber reinforced composite, you'd be talking of, let's say, a range which is of the order of 10 times the diameter of the fiber or whatever you're looking at. So the fiber diameter of the order of 10 microns, you're talking of about 100 micron sphere around that. And what is happening in that neighborhood can actually determine what is happening at that point which of interest. So the point of interest is that, and you have a spherical element around that, infinitesimally small spherical element, and then you're saying that whatever is happening in that neighborhood can also affect it. So it's not only epsilon KL at that particular point which is going to determine it, but epsilon KL at all those other locations around it could also determine what is happening at that particular point. Is that clear?
Yes, sir.
Yeah. Any other questions? Okay. So let's go back. So this is the elastic material. That's the first assumption that you have, where you're saying that the stress is a function only of the strain, and the strain at that particular location at that particular instant of time. So that's all that the elastic material says. All that you're basically saying is that this particular relationship holds, that is sigma ij is equal to sigma ij of epsilon KL, but we have not made any assumption about the mathematical form of this particular equation. So in other words, we are saying that it could be nonlinear elasticity as well. In other words, the dependence on sigma ij can be nonlinear with respect to epsilon KL, which is why I specifically drew this curve, if you see, as not a straight line but a curve, sigma ij versus epsilon KL, because in general you can see that it can be nonlinear over here. Okay, so it could be a curve. Now we come to the second aspect that we want to deal with over here. The second assumption. Yeah, that is material linearity. And again, I'm using a particular color code over here. When I say green, it says that for most practical applications of light vehicle structures, it is an acceptable approximation or assumption in the range that you are interested in. Because remember, we talked about two questions over here. One is whether about the necessity of the assumption. The other is in terms of the relevance of that assumption. So that's what we are saying. It's both necessary as well as relevant in order to derive a lot of things that we are deriving. Therefore, I use a green font here for elastic material. Now coming to the second aspect, we're going to talk of material linearity. That's in a yellow font, which says that yes, sometimes it is necessary and relevant, sometimes it may not be. Okay. For example, if you're dealing with materials which are stressed beyond a certain point, you might go into the nonlinear regimes. In fact, that would happen in the elastic case as well, go beyond the elastic regimes sometimes. But for most part, we are going to consider polymer matrix composites. When we are considering polymer matrix composites, we are talking of a brittle nature, and therefore it would not have anything beyond the elastic limit. It would fail before it gets into anything like that, into a plastic regime, etc. So that's what we are focusing on. But of course, we are dealing with metal matrix composites or metals per se. We need to look at the elastic assumption also to some extent. But for many things that we'll be deriving, the elastic material is a reasonably good assumption within the scope of this course. And material linearity is also. But for a few applications in flight vehicle structures, you have to go beyond this material linearity. So now let's again come back to... so now what we're talking about here is material linearity, that basically that function that we had taken, sigma ij, we said that it depends only on epsilon KL. Oops. Epsilon KL, but that was a nonlinear dependence. Now with material linearity, what we are saying is that this is basically a material property. How the stress behaves with strain will change once you change the strain. So in other words, this curve that you saw over here, this curve will be different for different materials, even when you choose a specific value for I, J, K, and L. So in other words, it's basically a material property. So when you're saying material linearity from this context, we are referring to this particular relationship becoming linear. So this becomes linear in the sense that now we are going to talk of a sigma ij, which is going to be linearly dependent on epsilon KL, which is nothing but a generalization of your Hooke's law. So Hooke's law, you said that sigma is equal to E times epsilon. Now again, let's introduce that quantity E. But now we are talking of 9 different components over here and 9 different components over here. So you cannot have a single E which takes care of all of that in a general problem. So you will have the strain which is related to a particular stress. So the stress which is related to a particular strain. Okay, so now there are a few concepts that I'm trying to introduce over here. Now you see that unlike sigma and epsilon, for which 2 subscripts were sufficient, this quantity E that we have introduced, which is basically nothing but a generalized Hooke's law, this particular quantity that we are introduced requires 4 indices, which are I, J, K and L. Okay, and like all other Latin indices, this also has the range 1, 2 and 3. So this is the range through which each one of them can take, and therefore the number of components here was 3 into 3, 9 for the stress and the strain. Here you can have 3 into 3 into 3 into 3, a total of 81 elements of this E. And what this is saying through a linear model is that all of these are constants. In other words, they don't change with the strain. So if you increase the strain also, E remains constant. So in other words, the relationship between the stress and the strain, that is the stress and the strain, remains the same whatever the strain value might be. So whereas in reality what happens is, as the strain starts picking up, the strain can affect the stress in a non-linear fashion, and therefore your EIJKL can in general be functions of epsilon KL, which is not something that we are considering over here. So that's what is meant by material linearity, that we are saying that these 81 parameters are constant.
So by saying this, are you pointing out that in the previous case when the elastic non-linearity was there in the curve, in that case the Young's modulus was changing?
That's correct. So in general, it can change, but of course this is a special case of this. Okay, so what we are having here is just a special case. Okay, so this is included in that, because any nonlinear model, linearity is a special case of that. Like how we are saying that metal can be considered as a special case of composites for various applications, as long as you're not going beyond the elastic limit, etc. It can be considered as a special case because you're instead of anisotropy we are having isotropy, instead of non-homogeneity we are having homogeneity. Same way, the nonlinear elastic model says sigma ij depends on this in a nonlinear fashion, whereas a special case of that is linearity, where we are saying that this is the actual dependence, that functional form that we are talking about, how sigma ij depends on epsilon KL, is now specifically mentioned to be EIJKL multiplied by epsilon KL, which is where the EIJKL are all constants, and therefore we are referring to material linearity. Okay?
Yes, I got it.
Yeah. Now there are a few other things that we want to mention over here. The fact that we need 4 indices over here means that we are talking of E being a, let me not use this, E being a 4th rank tensor, because it involves 4 directions. So it's a 4th rank tensor with 4 underlines. Four directions are important over here, 2 of which are associated with the stress and 2 of which are associated with the strain. And you see that I also have put the subscripts as well as superscripts over here, instead of putting them all together as IJKL, either a subscript or superscript. Now this has a particular relevance in the case of tensorial notations as well, in terms of the components that are involved. When we use subscripts, we refer to what are known as, let me just go to a new. Okay, so when we refer to subscripts, we are basically talking of what are known as covariants. And when we are referring to superscripts, we are talking of what are known as contravariants. What does this mean? Very simple. You just go from the meaning of the word itself. What does co mean? Co means with, together. And what does variant mean? It's varying. So it's varying along with something else. So that's basically what we are talking about over here. Something is varying along with. On the other hand, contra is something that we are talking about contradictory. And in a mathematical sense, what we are talking of is in an orthogonal sense compared to the covariant. So the variation that is happening, again there is a variant, which means it's also varying. But now the variation is actually happening in a orthogonal sense. Now for Cartesian coordinate systems, you would see not too much of a difference between these. But once you go into non-orthogonal systems and curvilinear coordinate systems, you would see there is a subtle difference between that. And to keep that generality in mind, we are using this. But there's also one more reason why we are using that. And that is because we are introducing a concept of what is known as an implied summation. So you see that this KL that is there in the strain is having subscripts rather than superscripts, whereas this KL is having superscripts for the E. So when you have repeated indices, those repeated indices indicate that there is an implied summation over that repeated index. In other words, you are going to have these K and L summed over their ranges, which is 1 to 3. So in effect, what we are trying to say there is that sigma ij is equal to a summation over K equal to 1 to 3, a summation over L equal to 1 to 3 of Eij KL into epsilon KL. So once that summation is over, you see that I and J continue to remain, whereas K and L have been summed over and have been dropped. And that is what you have on the left hand side as well, I and J. So in other words, these are called as the free indices, so which are fixed for a particular equation, sigma ij, let's say sigma 1, 1. And then on the other hand, these indices KL are called as the dummy indices. Because you might as well replace KL by something else like MN, etc. But because all that you're doing is just summing over the entire range, which in this particular case happens to be 1 to 3. So this is the most general form in which linear material elasticity can be put up for the non-local, non-memory case, where you're basically having the stress depending only on the strain, but that dependence now is entirely linear because we are talking of these E's being constants to be determined experimentally. Okay, so this is what linear elastic material means. Are these two assumptions quite clear? We need to make actually 10 assumptions, of which we have made 2. So in the next class, we'll look at making the other 8 assumptions. But if there are any questions related to these 2 assumptions, I'd be happy to take, because this is very, very fundamental. And you would have probably seen various aspects of this in various courses. but I wanted to put it all together in a particular form in which it will be useful for us going forward in this course. So any questions? I'd be happy to answer that.
Sir, I'm having one. Sir, actually, these both statements are contradictory, sir. Because when we say the material is linear elastic, so first you explain first you explain elasticity, then you explain linear materials. Okay. So in both the cases, in the first one, the elastic thing, the Young's modulus was changing because because it is a curve. And in the second one, the Young's modulus is a constant. When we say the material is both linear and elastic, so then how the Young's modulus is changing?
So now you no longer have a curve, you would have a straight line. When you plot any one of these sigma ij with respect to epsilon kl, and remember this is a straight line which is a curve as well. It's a special case of a curve. So here we said that with only the elastic assumption over here, we were saying that it can be any curve. Okay. Now all that we are saying is that that curve has to be a straight line. So we are making a further contraction in the class of problems that we can deal with, which is still okay, because a lot of the materials that we'll be dealing with will obey this. So there's no contradiction there.
Sir.
What contradiction do you see?
No, sir. I was just saying that in the first case, when we only say the material is elastic, then the curve, then there is a curve, and when we say the material is linear material, then the curve is straight.
Yeah.
Now the contradiction comes when we say the material is linear elastic. So I was thinking, if both things are there, then how the Young's modulus will vary.
No.
But now it is clear. It is a straight line.
Yeah. So what I'm doing is I'm adding up the assumptions. I'm not looking at each one of them individually. I'm saying already the material is assumed to be elastic, non-local, without memory. And for such a material, again, I'm reducing the subdomain of materials of interest where that behavior is linear. So you can have in general various combinations, like you can have linear elastic, which is what we will be dealing with. You can have non-linear elastic, which is what we had shown in that first picture. That is basically this. We had shown the non-linear elastic. So this is basically that. And the linear elastic is over here. Okay. You can also have non-linear inelastic, in which case the loading and unloading are not along the same curve. It can come back along a different curve. That is basically what you're talking about as inelastic over there. So
exactly, sir. So I was also thinking about this plastic strain accumulation.
Okay.
I mean, the linearity, even the linearity is only a part of a small loading and unloading curve during the tensile and the compressive.
That's right. Yeah. And that is good enough for most materials that we deal with. Even though they are going through very large deformations, the strains still remain well within the material failure limits, which for most composites would be of the order of 2% or so before they have a brittle fracture. And therefore, within that limit, you would always see that the stress strain curves are linear. So for a healthy composite structure applied to flight vehicle components, you can always live with a linear elastic model, which is non-local and which is not having a memory built into it. And the memory can be in the form of, for certain materials, in terms of the strain rate. For example, impact problems, the high strain rate can influence how this stress strain behavior is. It will be very different at high strain rate as compared to a low strain rate, and various other things like the what is the thermal cycles it has gone through, and therefore does it have any creep, what is the mechanical or thermal loadings cycles that it has gone through, and therefore what is the fatigue, and therefore what is the remnant strength that it has, and therefore which will limit how far this can go. it might stop at a certain location here itself instead of going all the way to this particular strain value over here. So these are things that are essential in understanding failure or damage mechanics. But as long as we are dealing with healthy structures, the materially linear elastic model is more than enough for a lot of the analysis and even design that we go through. Yeah? Any other questions?
Sir,
yeah.
So, in the elastic material assumption, we assume that the stress at a point depends only on the strain.
Correct.
The thing that what I want to know is the strain. I mean, direction of the strain, does it matter? Like, for example, if sigma 11, does it depends only on epsilon 11, or does it depends on all the epsilon epsilon k?
Yeah, good question. Wait for the next class in terms of the other assumptions. But at this stage, when we have made only elastic and linear, we are saying that every one of the sigma ij depends on every other epsilon kl. There are 9 each, and so you have, as we said, there are 81 constants over here, and each one of those constants can be non-zero. So therefore, every epsilon can in general have an influence on the stress component that you are interested in. So 9 for each stress component, it depends on each of the 9 strain components. Okay, so this is the generic level at which we are. We will include certain aspects from the speciality of the material in terms of its geometry and in terms of the planes of symmetry involved to reduce this further. But at this stage, where we are only saying that it's elastic, non-local, no memory, material linearity, you can have in general all these 81 constants being non-zero. So every stress component depends on every other strain component apart from its own kind.
Okay, sir.
Okay. Yeah. Anybody else? Any questions?
Hello, sir.
Yes.
Sir, you have mentioned this IJ. These are covariants, and then you have mentioned these are also free indices. So actually, these are synonyms, right?
Come again. Covariant and which are synonymous?
This free indices.
No. Let's see. See, the covariant and contravariant are basically geometric features. Okay. So you're basically saying that something is varying along with a curve. Okay. So let's introduce, let's say, a coordinate system x1. Oops. X3 over here, right? So what we are saying is that a covariant is always tangential to this. It goes parallel to whatever coordinate curve that you have. Here I've shown x1, x2, x3 as straight lines, but in general they can be coordinate curves like these. And here I've shown it as orthogonal, but in general they can be some curves like this. So let's call this as, let's say, y1, y2, y3. So anything which varies tangentially along the curves is covariant. Anything which varies in an orthogonal plane to that is basically contravariant. So in a plane which is perpendicular to this curve x2, whatever unit vectors that you introduce over there are contravariant. Is this clear? On the other hand, the indices that we are talking about here is just a notation that we are having. The free indices are those over which no summation is involved, because they are the ones which are on the left hand side, so they are fixed. So at a particular time I might be interested in a particular component, let's say sigma 2 3. So I've already fixed I to be 2 and j to be 3. So they do not vary. Okay. So on the other hand, these are dummy indices KL that you see in the superscript of E as well as a subscript of epsilon, and those, because they are repeated, there is an implied summation according to Einstein's summation convention, and therefore they are dummy because you're only using them to say that you have to sum over their entire ranges, which in this particular case happens to be 1 to 3. So even when I do not write these summations explicitly, that's what is understood. So you do not need to specifically mention that, which is what this form of the equation is over here. Okay, so I do not need to put those sigmas over there ahead of the right hand side, because KL is repeated, once upstairs, once downstairs. Upstairs in the case of this, and downstairs here, what we also call as superscripts and subscripts, and which we also call as contravariant and covariant. So these are all, for the practical purposes of this course, synonyms. When we say contravariant, superscript or upstairs, it means the same. Same way downstairs, subscript or covariant means the same. But there is a lot of mathematical geometry that is involved over here in terms of what we are talking about is basically tangential in the case of the covariants, because they are varying along with the coordinate curves. So this is varying with, which is why we use co. Whereas this is varying orthogonal to the coordinate curves. So that is the reason why we are saying that it is covariant and contravariant. Okay, there's more to covariant and contravariant than just the fact that these are dummy indices. Yes, the dummy indices need to be, one of them has to be covariant, the other has to be contravariant for an implied summation to take place. Some people just ignore that and just say, even write this as, in this case, just sigma 2 3 KL epsilon KL, writing the KL also as subscript, which is not the right thing to do, because there's no implied summation if you're just writing it in the both in the subscript, because both of these are covariant. So this is not right. Okay, so what we are saying is that yes, what is there on the left hand side is fixed, which is what is 2 3 over here, and that's why we're calling that as the free. The other ones we are calling it as the dummy, and the dummies need necessarily to be one upstairs and one downstairs, only then the implied summation takes place. But you would see in many textbooks and even papers, sometimes this is not very rigorously followed, but it's important for you to know that this is what the rigorous notation is.
So basically, this covariance and contravariance, these are some physical parameters, right?
Correct. They are actually geometric parameters, not physical, but geometric, because you are saying that with the coordinate geometry that you have introduced, what is varying with that coordinate curve and what is not varying with that coordinate curve, which is varying orthogonally to that coordinate curve. So that's basically what you're introducing. When you go for a Cartesian coordinate frame, x1, x2, x3, that what is shown over here, then they would lose their differences. The the coordinate systems, covariant and contravariant, can become identical to one another. It's only when you go for non-orthogonal curvilinear systems you would see the difference coming in. So that's a generic case that we are doing, and if we use that, that would be a special case of that would become the Cartesian coordinate frame, which is orthogonal set of unit vectors.
Okay, right, sir. Thank you.
Okay, welcome. Anybody else? Okay, thank you very much. So we'll meet next week on Tuesday. Wish you all a very brilliant Diwali, in the sense that its light represents knowledge. So the movement from darkness to light is a symbol of moving from ignorance to knowledge, or from one level of knowledge rather to a higher level of knowledge. So I wish you all the best for the 4-day long weekend Diwali that you have, starting from Dhanteras tomorrow to the Naraka Chaturdashi on Saturday, and Sunday being the Deepavali Amavasya, and Monday being the Bali Padyami. So they all have their own interesting significance from a knowledge perspective as well. So wish you a great long weekend, and see you on Tuesday.
Thank you, sir. Happy Diwali, sir.
Thank you. Thank you very much.
Happy Diwali, sir.
Thank you so much.
Happy Diwali, sir.
Thank you.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वानवयजामहे
So I'm doing it on an iPad where I'm not able to download the attendance list. So if you can do that and send it to me, it will be great.